Finishing us off here will be Erol Kaslan from Caltrans. He's the Chief of Structures Investigation for the North Caltrans Division of Maintenance. Erol will discuss joint elimination practices at California DOT. He's the structural maintenance engineer.
In any case, my name is Erol Kaslan. As Dick said, I work as the chief of our structure investigations unit in Northern California for structure maintenance and investigations. And I'd like to give you perspective of California's practices, or perhaps just our overall strategies for eliminating bridge joints. And so with that, I talk a little bit about our bridge structures, our structure types, and the joints that we use, giving a general overview, and then daylight some considerations for bridge joint use in California, touching on the overall performance, some seismic considerations, and the future use. Without any delay, we'd like to start off with California bridges and bridge joints. California's predominant bridge structure type is continuous cast-in-place concrete, and has been for quite some time since the interstate era. Some 82% of our state bridge inventory is continuous cast-in-place concrete, and there's some statistics there on the screen of how many we have. Continuous concrete bridge designs are desirable and have been for overall structure efficiency and performance, and we've used them widely since the 1950s, and certainly in the heyday of our bridge construction efforts post-interstate area in the 60s and 70s and into the 80s. That was our predominant, and remains our predominant bridge structure type. By virtue of their design, our continuous spans naturally reduce the number of joints typical with simple spans designs. Most of these designs facilitate, abutment joints with regular seat type abutments, and in some cases integral abutments to relieve temperature movements, creep shrinkage, pre-stress shortening, and so forth. When necessary, in-span joints have historically been provided at superstructure inflection points via a seat type hinge. And by virtue of our designs, we don't have very many. When we do have them, they are at the abutments, and in some cases in the past, we've used in-span hinges. And I would like to talk about that a little bit more in a moment. There's a picture of our bread and butter California cast-in-place pre-stressed box girder. If you've ever been out to the West Coast, I'm sure you've seen plenty of these. And of course, this continuous design here is typical of what I've been mentioning with the seat type abutments shown. I wanted to show a picture, though. It's not all about pre-stressed box girders here in California. A fair amount of our inventory is continuous RC, or reinforced concrete T-beams. Bridge in Northern California, some 400 feet long, showing a continuous design. This goes back to the mid-1960s, and we're showing continuous, of course, over the supports and integral with the supports here. Again, not an unusual design for us. I wanted to show another quick photograph of a typical 1960s era reinforced concrete box girder. This is, many of our bridges are configured like this, but this shows what an in-span hinge looks like. This is at the inflection point here. A close-up of the hinge shows a couple of things I'd like to point out. One, of course, is some distress that's noted there, in which I can talk about in a moment. Some damage and distress at that, but most notably is the very short seat length. The seat length on this bridge in the 60s, about 8 inches or so. We used to build them as little as 6, and sometimes as greater as 10. There's no way that we would ever construct a modern seat type hinge, in-span hinge with a seat length this small. The current minimum length for seismic considerations is 30 inches. But I wanted to show you just what we were doing in the past and what is out there on our inventory now. Caltrans' use of bridge joints. Well, contrary to what some of our other state partners are doing out there, Caltrans does not currently maintain a deliberate policy to eliminate bridge joints from maintenance considerations, right? That's not forefront. There's no policy statement that says that anywhere. However, I'll demonstrate by virtue of some of our practices that we're getting rid of them anyway. We use them when we have to, and we're seeking to minimize them. Abutment joints are most commonly used to accommodate expansion and contraction. Those are accommodated, by using a seat type abutment, or L-shaped abutment as it was called. In some cases, we do use an integral abutment, and the rotation and translation is taken care of either at the piles, or the bridge is just designed to accept that. In-span hinge joints, as I mentioned, were used, historically for service load conditions. However, they are still allowed and may potentially be used to allow independent displacement of adjacent bridge frames during an earthquake, right? It's in the tool bag of the designers that could be used to allow for seismic considerations, seismic design considerations, and I'll talk more about that in a moment. There's no doubt that bridge joints are a routine maintenance item for Caltrans. We've spent about $10 million a year over the last 5 years on joint and joint seal maintenance projects, about 10–11% of our annual allocations for that. So it is a hit. It is a routine item of maintenance. A large percentage of that cost, I'd like to point out, goes to traffic control. And so when we do go in and do any kind of bridge joint maintenance or bridge joint or joint seal replacement, we typically programmatically replace all the joints on a bridge under the same contract, just because the bulk of the cost goes really through the traffic control. So joint performance. Speaking of joint performance in California, our abutment joints generally perform pretty well. And the joints are very serviceable. And what I mean by that is that we can get at them. If we need to do any maintenance, it's easier to do it than it would be over a column support or a bench support. And so I think for that reason, we do accept the presence of abutment joints and as being a serviceable detail and an acceptable detail for us. In-span hinge joint performance has been generally satisfactory, but it also has been problematic for us in the past. These don't perform quite as well as the abutment joints. These things are hard to build, and certainly the original designs and the original construction projects in the 60s had their problems with construction quality. Also, like any joint, moisture and associated corrosion-driven distress can be a real problem there, difficult to deal with. In some cases, excess pre-stress shortening will occur at some of these hinge joints, opening them up and leading to a premature bearing failure or a shortening of the seat width that can give rise to some of the damage that I may have shown you earlier in an earlier slide. Certainly, in-span hinge joints can lead to some undesirable seismic performance and have in the past. This is associated with some adjacent frame pounding. The frames on either side of the in-span hinge joint can pound into one another. That's a real problem. And certainly, unseating is something that has been a problem for us in the past and that we seek to mitigate with our current seismic design criteria. Overall, in my shop in bridge maintenance, we consider hinge joints to be difficult, and they're expensive to service. They're difficult to maintain. Our earliest designs that we built a lot of in the 60s made the bearings. They buried the bearings in the hinge joint diaphragms where we can't get at them. So any failure of the bridge bearings at a hinge joint probably mean we're just accepting that. In cases where we can't, we need to get in and demolish the bridge joint, the in-span bridge joint. We need to provide an extensive temporary support mechanism and close the bridge down because we can't do it in a stage construction fashion. So overall, considering this, when we go through our type selection process for newer bridges, our current bridge designs generally seek to minimize the use of in-span hinge joints, and really that's to reduce maintenance and improve overall structure efficiency. So that's kind of where we are with the performance and what we're doing. A couple of quick photographs showing a hinge reconstruction project that we had in San Francisco at a long viaduct in south of San Francisco. You see the temporary support, full temporary support of the areas adjacent to the hinge, as well as the adjacent span. That project going forward, that was a hurry-up project that required the complete closure of the structure, quite difficult to do. Another photograph here on the right side of your screen shows what can happen when a hinge joint goes bad and you're waiting for a construction contract to mitigate. We erect a temporary support underneath the long supported side of a hinge, and that example was just outside of Sacramento. I actually want to point out in this photograph, there's a little column here that seems unusual around a hinge joint, and that's because it is. You can see the distress, a lot of efflorescence and staining and rusting at this joint. This was an example where a joint, while being constructed in the 60s, had a lot of problems during the construction sequencing, to the point to where the construction engineers were not comfortable with it, and they erected this, what we call this peg leg column here, just to kind of help support the hinge joint where they could. That actually served us well for about 25 years until the joint and the hinge completely failed. I want to talk a little bit about some seismic considerations of in-span hinges. This is something that is certainly on our mind in California. We have earthquakes here, and the earthquakes have caused some substantial structure and bridge damage in the past. That tends to be at the forefront of our design considerations for all bridge designs, at least certainly an extremely important design consideration for our bridges. In general, the seismic considerations, well, our in-span hinges are typically designed for the surface loading conditions, but they're always checked for the effects of seismic loading. So even though a hinge joint may be desirable for temperature and other longitudinal effects, it's got to be checked for the effects of seismic. The support length, as I mentioned earlier, of the hinge seat needs to accommodate all the anticipated thermal movement, shortening, creep, and shrinkage on top of the relative longitudinal earthquake displacement demand between adjacent frames. And so even in the lowest demands, the minimum support length of an in-span hinge joint is 30 inches. Certainly could be much more depending on the location and the analysis of the bridge. And keep in mind, that's just the support length of the hinge. You had diaphragms on either side of that, and we could have something in the order of, 10 feet of hinge that needs to get built out there in the minimum conditions. Certainly in-span hinges do allow each frame to displace independently during an earthquake. That can be both a good thing and a bad thing, depending on the design perspective and the unique case-by-case basis that the designer considers. Certainly, we know that large relative displacements can develop if the displacements of the bridge frames are out of phase. That is, if the natural periods of the bridge frames on either side of a hinge joint are such that they will move differentially to one another, that can be a problem. So our designs must consider the fundamental periods between adjacent frames on either side of the hinge joint to prevent unbalanced loading of one frame by the other. Right. So I know I talked a lot there, but that's just kind of is some of the considerations that we have. There's some more though. Overall, the best way to increase a structure's likelihood of responding to seismic attack is to balance its stiffness and mass distribution between frames. That has become apparent. Certainly learned a lot since 1994 on that, the Northridge earthquake. The consequences of an unbalanced frame really include a greater likelihood of out-of-phase response between the adjacent frames, and that can lead to large relative displacements that increase the probability of a longitudinal unseating or pounding between the frames of the hinge joints. That's really what it is there. If the frames are not balanced on either side of the hinge, the frames can move differentially to one another, either pound into one another or on either side, or actually unseat. Certainly the pounding of an adjacent frame, greatly undesirable, as it's going to transfer the seismic demand of one frame to the other, which in combination with the relative translation may exceed the standalone capacity of the frame. So, just some of the things that our designers consider. If they're going to have a hinge joint, there's some consequences to that, and they need to kind of keep that in mind. Here's a graphic out of our seismic design criteria manual that just shows an example of balancing frames, a mass stiffness balance on either side of an in-span hinge joint here, kind of giving an idea of how a designer must approach the problem. And you can see here the column lengths, differing heights, therefore differing stiffnesses, the span lengths being longer on one side, shorter on the other, balancing mass. And so the one frame to the next, their attempt is to balance that, have a balanced mass stiffness ratio on either side. And really, this is a graphic that many of you may have seen before, but this is the reason why we're trying to balance those frames. We don't want to have an unseating at an in-span hinge. Now, there's a lot going on here. There's a heavy skew and a lot of other things going on, but it's a fairly dramatic photograph that shows what happens to a span when a bridge in-span hinge seat unseats. This is the Gavin Canyon undercrossing after the Northridge earthquake in 1994. So what does our seismic criteria say? I gave you some considerations, seismic considerations of joints, but what does our SDC say? Well, the seismic design criteria, or SDC, really doesn't encourage or discourage the use of bridge joints or in-span hinges, right? It doesn't say you shall do it or you shouldn't do it, but it does require a lot of other stuff. It does require superstructure continuity over the support, something that we have had for quite some time with most of our bridge designs, but now it's an absolute requirement. It notes that continuity provided by the deck slab alone is insufficient for the requirement. Right? So a lot of our earlier designs provided for what we called simply supported for self-weight, continuous for live load. That design philosophy or principle now is insufficient to meet the SDC. The SDC in-span hinge support length requirements and the associated internal shear key requirements are substantial. As I mentioned, they're big. And what that means is that an in-span hinge can add a lot to the cost of a bridge because they're really quite large, very difficult to construct, or quite congested with a lot of reinforcement. As such, there's a consequence there. And as a consequence of that, our designers are favoring other mitigations to balance frames, such as isolation casings for structure supports, in some cases isolation bearings, or other connection detailing that can be used in lieu of an in-span hinge. Here's a brief graphic kind of showing the principle of a isolation casing as an alternative design strategy to balance frames. In this case, the principle is where a structure support, the effective column length is kept about equal amongst the frames by isolating the column or the in-soil support against the surrounding soils by the use of a casing. That's becoming very popular for our newer bridge designs. Just a couple of photographs here. I wanted to show some of our newer bridge designs that don't use joints, or at least keep the joints at the abutment. This total structure length here in excess of 600 feet, of course, showing no joints over the supports. We do have joints at the abutments, and in this case, the design is working out quite well for us. This is Eel River in Mendocino County, Northern California. This example here, a bridge that constructed over Lake Shasta, Northern California, some 2,000 feet of bridge length. No in-span hinges or intermediate joints provided. The only joints here at the abutments, and again, those are also performing quite well. So a couple of examples of where we're going. I was notified by one of our design seniors that we currently have a bridge under construction in Northern California that is over 1,000 feet long. Again, no intermediate joints, and going for a jointless construction just by design. Well, touching on the future use of bridge joints in California, our bridge designs, including our ABC projects, are going to likely continue to use abutment joints. They're good performing for us. We can get to them. Although I know some designers are investigating the use of a slab where we move the abutment joint off the bridge and move it onto the approach bills, that has been shown here and by some of the other panelists. The use of link slabs. Well, kind of the jury's still out with link slabs here in California. As I mentioned, our SDC requires superstructure continuity over the supports. That means the tops and bottoms flanges are going to be continuous over the supports for our designs by seismic criteria. Link slab is not going to provide that as a standalone, and so the consideration of link slabs and how it works with our SDC is still under our internal review, and we're looking at that. Something that I wanted to daylight that may be of interest to you is that we are developing a design criteria for tsunami resistance for our coastal bridges. This design criteria will require continuity and connectivity of the superstructure to the substructure at the supports. And so, with all these considerations that I've put forward, our continuous designs, sketchy performance of some of our earlier in-span hinge designs, the seismic considerations for use of an in-span hinge design, so on and so forth. We expect in the future that our joint use is going to continue to be minimized for overall structure performance. That's our anticipation. I don't see us eliminating them yet, but of course, the next generation of designers may start moving in that direction. And so with that, I've been talking a long time. I'll go ahead and conclude. I want to thank you, and there's ample time for, I think, at the end here for some questions and discussions. So thanks very much.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.